This video is going to go through our quiz review for student learning tasks 13 to 16 in the polynomials topic of our quadratic and polynomial unit, Unit 2. So this is again the Unit 2 Topic 1 quiz review. If you are going to follow the entire video and take notes, my suggestion is that you do so on a separate sheet of paper and then use your quiz review later and try the problems a second time. So here we go. The first thing we're asked to do is add together f of x and g of x. G of x is 3x squared plus 4x minus 5. G of x is x cubed plus 2x plus 1. I want you to notice I didn't use parentheses here. I'm just adding. So really what I'm going to do is just collect my like terms. I see I only have one x cubed term. So I have x cubed, and then I have one x squared term. So I've taken care of these. Now I have 4x and 2x, so that becomes 6x, not 6x squared. 4x plus 2x is just 6x. And then negative 5 plus 1 is negative 4. Okay, number 2 is g of x minus f of x. So now I am going to use parentheses. I'm going to say g of x, x cubed, plus 2x plus 1, minus f of x, 3x squared plus 4x minus 5. And the next thing I'm going to do is I'm going to switch my pen color, and I'm going to distribute this minus sign, and I'm going to subtract all of f of x. And the reason I'm doing that is that I don't want to forget about the 4x and the minus 5, that I'm subtracting those also. A lot of times we have the tendency of just subtracting the first term. So I'm going to turn this into a plus, and I'm going to distribute that minus sign to everything. And because the 5 is already we're already subtracting it, when we subtract a negative, it turns into addition. So here we go. Now I'm just going to pretend the parentheses aren't there. I could rewrite the problem, but I'm not going to because, you know. And minus 3x squared minus 2x, because the 2x minus 4x, and then plus 6. So now we're going to do something similar for number 3, f of x is 3x squared plus 4x minus 5. M of x is negative 3x plus 7. So again, I'm going to switch my pen color. I'm going to turn this into addition. This becomes addition. This becomes subtraction. And I get 3x squared plus 7x minus 12. So those are the addition and subtraction of polynomials. 4, 5, and 6 is the, well, 6 is addition also. But here we've got some multiplication, so let's take a look. Number 6 is asking us to multiply f of x and h of x. So I notice f of x is 3 terms and h of x is 2 terms. You have a lot of different options here. You can just distribute. You can use the box method. It's really up to you. I'm just going to distribute. So I've got 3x squared plus 4x minus 5 times x squared minus 8. So first, I'm going to distribute everything here. And I've got 3x squared, whoops, to the fourth, add the powers, minus 24x squared. Then I'm going to go, this is going to be ugly, 4x times x squared is 4x cubed. 4x times minus 8 becomes negative 32x. And last, I'm going to do the 5. Minus 5 times x squared becomes minus 5x squared. Minus 5 times minus 8 becomes plus 40. And now I'm just going to put my like terms together. I'm going to just look real carefully. I've got 3x to the fourth. I've got 4x cubed. I've got negative 29x squared. As a reminder, when we combine like terms, we're literally just collecting how many x squareds we have. The square does not change. And then minus 32x plus 40. M of x, g of x times m of x. So now again, I've got 3 terms, x cubed. Let me move that down a little bit, actually. There. Purple is nice. we're going to go x cubed plus 2x plus 1 times m of x, which is negative 3x plus 7. So I'm going to do this a little differently than I did the first one. The first time I distributed each of the trinomial to each of the binomial. Here I'm going to go a little bit backwards just to show you that like it really doesn't matter. I'm going to do negative 3x times each of these, which gives me negative 3x to the fourth minus 6x squared minus 3x, and then I'm going to go 7 times each one, and that's going to give me, and I'm going to show you a technique I use sometimes. No, I'm not. I was going to stack them, but there's no other x cubed there. Sadness, little x cubed. He has no friends. 7 times x cubed. 7 times 2x. 7 times 1. I'm going to put my like terms together. I only have one x to the fourth term. I only have one x cubed term. I only have one x squared term. I have two x terms, so that becomes plus 11x, and then the plus 7. So that's number 5. Number 6 is asking us to add together h of x and m of x. H of x, and again, I don't need parentheses for this. I'm really just collecting like terms. I'm going to have x squared minus 8 plus negative 3x plus 7, and I get x squared minus 3x minus 1. Boom. Oops. All right, our next set of problems is asking us to factor, and I'm going to give you a really quick review of our factoring flowchart, and then we're going to get into the factoring. As a reminder, at the very top of our factoring flowchart, we always look for a greatest common factor first. That's the first thing we're going to do. And then we have 3 situations. We could have a binomial, a trinomial, or a polynomial. If it's a binomial, we have 2 options. Maybe it's the difference of perfect squares. Maybe. Maybe it's the sum or difference of cubes. And that's where we would use SOAP and square the first, multiply them together, square the second. Now, if it's a trinomial, we have 2 situations. We have a equals 1, which is just the add and multiply method. And then we have a is not equal to 1, which would lead us to either box or split the middle. S-P-L-I, there we go. Box or split. And if it's polynomial, if we have 4 terms, we're going to see, does it group? It might not. So I'm going to work this flowchart for each of these problems. Number 7, the first thing I'm going to do is, does it have a greatest common factor? Yes, it does. Both terms contain an x, so I'm going to factor out the x. If you want to write like over x, you can, but you don't have to. So if I divide each term by x, I'm left with x times x to the fourth minus 36. I have to have the x out there because it has to be, like, the product has to be the same as x to the fifth minus 36x. So now the question is, x to the fourth minus 36, is that perfect squares, the difference of perfect squares, or is it the sum or difference of cubes? And the answer is, it is the difference of perfect squares. I'm going to keep the x. X to the fourth is x squared squared. 36 is 6 squared. So now the question is, are either of these the sum or difference of perfect squares, or the sum or difference of perfect cubes, or the difference of perfect squares? Well, they're definitely not cubes. The first binomial has an addition sign, so it's out. The second binomial is x squared minus, but then this is a 6. That's not a perfect square number, so that is how I know that this is my final factorization. Number 8, again, I'm going to look for a greatest common factor first, and I notice that all 4 terms are divisible by 2. So that leaves us with x cubed minus 3x squared plus x minus 3. Now, I have the 4 terms that are left. That is a polynomial. So the question is, does it group? Let's see. When I look at just these 2 terms, I could take out an x squared. I'll bring the 2 down in a minute. If I take x squared out of the first two, I'm left with x minus 3. Well, that's exactly what I have right in my second group, so I'm just going to take out like an imaginary plus 1. Now I can rewrite this as 2, and now x squared plus 1 times x minus 3. And x squared plus 1 is addition, and that's not x cubed, it's x squared, so that's how I know it's done. Number 9, does it have a greatest common factor? No, nothing divides evenly into 27 and 8. Is it a binomial, a trinomial, or a polynomial? It's a binomial. So is this the difference of perfect squares or the sum or difference of perfect cubes? It's perfect cubes. So the question we're going to ask ourselves is, what is being cubed? What cubed gives us 27x cubed? 3x. What cubed gives us 8? 2. Now, I'm going to use that acronym SOAP. Same sign, this is minus, so this is minus. Opposite sign, always positive. Square the 3x. Multiply 3x and 2 together. Notice I'm looking at this as a 2, not a minus 2. Square the 2. And this is it. Once I factor using sum or difference of perfect cubes, you will never factor again. It just doesn't ever. Number 10 has a greatest common factor. Definitely an x. I don't think 1,000 is divisible, let's think, by 8. So I got 2 options here. I can take out a 2. No, wait, I think I can take out a... Yeah, I can divide 1,000 by 8. That's just 125. Now, I know some of you are thinking, but 8 and 1,000 are perfect cubes, but make sure you take out that common factor first. So I'm going to take out the 8x, and now I'm left with x cubed plus 125. So now I'm going to carry along the 8x, and 8 and x cubed plus 125, that's the sum of perfect cubes. It's going to be x and 5. Same sign, opposite sign, always positive. Square the x, multiply them together, square the 5. There we go. Number 11, I'm going to start 3 and 12 are both divisible by 3. And I've got x squared minus x to the 4th. Whoops. I've got x to the 4th minus 4. And that's the difference of perfect squares. So I'm going to have x squared plus 2, x squared minus 2. And this x squared minus 2 is not the difference of perfect squares because 2 is not a perfect square number. So that's done. You know, I think number 12 might be the only one has no greatest. Oh, I guess number 9 didn't have a common factor. But yeah, no common factor here. 4 terms. Let's go straight to grouping. What's the common factor out of the first 2 terms? X squared. So we'll take it out, and we're left with x plus 8. Now here, because this is a minus sign, I've said this before, if anytime you're grouping and the second group starts with minus, you're going to be taking out a negative number. And in this situation, we're going to take out -9, and we are left with x plus 8. So now I rewrite this as 2 binomials, and I've got x squared minus 9 times x plus 8. Don't put a box around it yet. Let's check. Are either of these binomials the sum or difference of cubes or the difference of perfect squares? Yes, x squared minus 9 is the difference of perfect squares. There we go. Okay, numbers 13 and 14 deal with multiplicity and behavior. So before I even start this problem, which is asking me for the multiplicity of each 0 and the end behavior, I'm going to really look at this polynomial. And I see that this polynomial has a leading coefficient of 1. It has a positive leading coefficient. That's important Now I'm going to look at the degree, and I see it's written in factored form. I have a squared here and a 1 here. Because it's written in factored form, I add these powers together. If it was written in standard form, I would just take the highest power. I'm going to say that again because that's a common mistake. Polynomials written in factored form, we will add the powers. Polynomials written in standard form, we just take the highest power. So like, for example, if we were looking here, if this was the problem we were looking at, the power is just 2. Power is just 3. The power is just 2. Those are our degrees because these polynomials are written in standard form. But when we are in factored form, we are going to add. So we end up with, that's ugly, a degree of 3. Why is this significant? If I have a positive leading coefficient and an odd degree, I know my end behavior models align with a positive slope. So I know that on the right, as x goes to infinity, y goes to infinity. And on the left, as x goes to negative infinity, y goes to negative infinity. That is going to help me. I'm just going to throw these arrows up here on my graph. That's going to help me determine the shape of my curve. So now, what is the multiplicity of each 0? I see 2 sets of parentheses here. There's no x out front, so no worries. My first 0 is -3, and I have 2 of them, so I'm going to write it twice. This means that this is a double root. What does that mean because it's a double root? That means it will be tangent to the x-axis. The second factor gives us a root of 5. 5 is a single root. Because it's a single root, nothing fancy happens. It just will cross the x-axis. Nothing fancy happens there. So I'm going to scale off my x-axis. 1, 2, 3. Please make sure you scale off your x-axis. And 1, 2, 3, 4, 5. Now, I know my end behavior here has to come up, and I know that 5 is a single root. So I know that my graph is just going to come straight through 5. I know that on the left side of -3, it has to be coming down, and I can't, watch this, I can't do this. Ooh, that was so ugly. I can't do this because I create another real root if I do that. So I need to remember that -3 is a double root. It's going to be tangent at -3. That's not terrible. Make sure it's clear that it's tangent, like make it big and fat and blobby if you need to. So there's number 13, the graph of f of x, which has a positive leading coefficient, an odd degree, and a double root. So we're gonna do the same thing for number 14. We're gonna start with the end behavior. Now I see a negative leading coefficient. This is a -1. Make a note of that. And again, I'm in factored form, so 2 plus 1 plus 3 is a degree of 6. Oh, I don't write that there. I was going to run out of space. Degree. If the degree is 6, that means it's even. So either it kind of resembles a parabola opening up or a parabola opening down. Because the leading coefficient is negative, I know my end behavior will model a parabola that opens down. So I know that on the right, as x goes to infinity, y goes, I don't want to write f of x, negative infinity. And the same thing happens on the left. As x goes to negative infinity, y will also go to negative infinity. So let's look at what kind of roots we have now that we know the graph goes down, down. We have 3 factors here. The first one gives us a 0 of 4, and there are 2 of them. So I know 4 is a double. I know that will be tangent at 4 because it's a double. I see I have a root of -1, and this 0 at -1 is a single 0. Then I've got x minus 2 to the third power, which means I have 1, 2, 3. Oh, whoops, I wrote the number 3. I have 3 2s, and that means that I'm going to have a change in concavity. That can be tricky to draw. So let's scale off our x-axis. So first off, I've got -1, and then I've got 1, 2, 3, 4. And I know that they're down, down. So when I graph this, the first thing I'm going to deal with is this change in concavity. And change in concavities when I'm going down on the right can look like this, or they can look like this. It's really up to you how you want to draw it. Now I'm going to do it the second way because I think it's going to be easier to connect to this double root. Oh, wait a minute. Hold on. 2 is the concavity change. 4 is tangent. All right, hold on a second. 4 is tangent. That makes that easy. That goes like that. Tangent at 4. Now, I'm going to have to swing this back up. So I'm going to kind of bring it like... You see how this kind of looks like... That could be a little smoother there. See how this kind of right here looks like a parabola opening up? This side needs to look like a parabola opening down. That's ugly. I can do better. And then I'm just going to bring it right through. Just make sure it's obvious that this is not straight. Like this is straight. Well, it's straight-ish. Make it obvious. And if you're not sure that you're a good sketcher, you can make me a little note and be like, this right here, I know I'm a bad drawer, Mrs. Strauss, but this is a change. I'm also a bad speller. Like, if you are not confident in your drawing skills, this is not art class. You can tell me it's a change in concavity on the graph like that, and I'll be like, oh, that's what that was trying to be. And we'll be good. Tangent one is easier. All right, so we've got one more of these graphs, and now we are in standard form. So, and you'll notice that I'm not asked for anything here. So what I'm going to do is I'm going to, on the side, make some notes. First thing I notice that I have a positive leading coefficient. And I have an odd degree because it's 3. That tells me my end behavior looks like this. Boom, boom. Now this is not factored, so I need to factor it. I notice that all the terms have an x, so I'm going to take that out. Then I have a trinomial inside. This trinomial has a leading coefficient that is not 1, which means I'm going to either need to box or split the middle. I'm going to box because I think that's what most of you watching this video prefer, even though I prefer to split the middle. So I'm going to go 3 times -4 is -12. And I need 2 numbers. They have to add to -11 and multiply to -12. That's not so bad. It's just -12 and 1. Now I'm real quick and build my little boxy box. Should have used this line tools because I can't draw a straight line. Oh, that's so bad. I've got 3x squared, -12x, 1x, and -4. So now, because I see both of these are negative, I know this has to be negative, and obviously this has to be the 4, because there's a 1 here, that has to be a 1x, makes this a 3x, makes this a 1. So my factorization is going to be x, and then 3x plus 1, x minus 4. And obviously you could switch those binomials. You could put the x minus 4 first. Now, why do I need to do the factoring? Because I need to know what my x-intercepts are, what my roots are. And here I see that I have x-intercepts, I have roots, I have zeros of 0 because of the greatest common factor, -1/3, and 4. And they're all single zeros. So this graph is going to be like a nice swooshy swoosh. I just have to get my x-intercepts labeled nicely. So I've got 0. I'm going to put this as -1, and then we'll put like, oh, that's really short. We'll make that like -1/3, 1, 2, 3, 4. So I'm going to come up and then straight down. And then back up again. And your graph could go lower than this, it's fine as long as the shape looks like this and they're all single roots. Again, if you followed me through every single problem, you should retry all the problems on your own without looking at your notes and complete all the problems until you can do them independently. Hope this video was helpful.